Okay, good morning. Good morning, first day of the week, Monday. So today, I'm going to show you an example of eccentric symmetrical bending. Okay. And then we're going to go into eccentric asymmetrical bending, a bit on the theory on that, which is not a lot. A reminder, quiz number 2 will be available tomorrow at about 10 o'clock. Okay, and the due date is January 28th, which is a Friday at 2359. Okay, now if you will go onto Avenue to Learn, I posted all these figures, okay, in week 3. So if you look at the content, week 3, all the figures will be there, and all these figures are the one that I'll be using. Okay, let's look at example number 1. It's going to be eccentric. Okay, so when we so what do I mean when I use the word, before we go to a question, what do I mean when we have the term eccentric? So a quick revision on where we finish off. Whereas eccentric, your stress formula will be equal to px over a, okay, minus by mz over izz multiplied by y. Okay, again I highlight, don't worry about the sign, whether is it plus or minus, look at the structure. Okay, right, so we know that in eccentric loading, there are two stresses are induced by two loading condition. One is, this is axial load, and the other one is based on bending moment. Okay, and this is okay. So for this case, we know that is eccentric loading. Okay, so we are going to analyze the stresses in section AA. Okay, so they put here is where section AA is, and that is the cross-sectional view. The one on the right is the cross-sectional view. Okay, so we are going to determine the stresses at point A and the stresses at point D, and the location of the neutral axis. So remember what I told you about neutral axis and geometry. So sorry, neutral axis and centroid. Okay, so centroid are determined based on geometry. Okay, whereas neutral axis are based on stress field distribution. Okay, and then very quickly, when the loading went in centric loading, centric symmetry loading, okay, position of centroid is also the same position of neutral axis. Okay, in centric loading. Okay, for eccentric loading, symmetry loading, the position of the centroid is not the same as the position of neutral axis. So you have to be careful over here. Okay, So coming back to our problem, okay, I'll let you guys copy. So by looking at a problem, we have to first construct our transformation. Okay, so the figure on the left, this is how the transformation look like. Okay, this is the y, x. Sorry, there's the y. This is the rotation about the z, and then on the section, so we are looking where we position ourselves at AA. This is our transformation. So this is y, z, and this is our rotation about x. Okay. So looking at the structure where the load and on the load on how it's applied, next thing that we're going to do is we're going to construct the deformation pattern. Okay, we're going to construct the deformation pattern. So I'm going to draw the deformation pattern in orange. Okay, so the deformation pattern will look like this. Okay, so this is how our structure will deform. Okay. And I'm going to construct our our centroid. Okay, well, I'm going to construct our centroid. So our centroid should look like this. Okay, after deformation. Okay. So this is our centroid. And the centroid before deformation, also in green. Okay. So this is also our centroid before deformation. Why I emphasis on the centroid? Because to get the moment about z is equal to p, okay, 50 times 10 to the power minus 3 plus by e. Okay, so e is the distance from here to here. Okay, that is my e, and e is the centroid. Okay, so e is the position of the centroid from the top of the cross section. Okay, anyone, any question? Are you okay with that? If you have any question, just speak up or type on the chat. I will check on the chat. Okay. So when we have done this, we will now know how the moment is applied. By looking at the deformation pattern, we know how the moment is applied. So I'm going to draw the applied moment. Okay. So this is our applied moment. And the other side, this is our applied moment. Okay. So the applied moment is in Z because the curvature of the moment over here and the curvature of the rotation about Z have the same curvature, right? They curve that way. So it's moment about Z. So from here, you can immediately identify where is the compression and where is the tension. So this is the compression. Over here will be tensile due to bending. Okay. So due to bending, we know at point A, right, due to bending, due to mz, right, if we know where the centroid is, so if this is our centroid, right, there's our centroid. We know the top due to moment about z, hold on, sorry, due to moment about z will be compression. Not compression of the Eugene. Come on, wake up. So down here will be compression. And up here of a tensile. Okay, so we know that. Okay, so this is how the analysis can help you first. Okay, then we know that is for the moment. How about due to the axial load? Okay, so we set out for the moment. We have to consider what is happening on the axial load. Okay, what is happening down here? Now the axial load can be tensile, also can be compression. Okay, I repeat again, the axial load can be in tensile, also can be in compression. So let's check what is it. Okay, so now if I'm going to draw our, okay, I'm going to sketch our structure. Okay, so this is how our structure look like. Yeah. So this is our section AA. Okay. So we know that P is in this direction, right? And AA is where we fix. Okay, we don't allow it to move, right? So this is where you have moment in Z, which we have stated, and this is also our counter moment in Z, right? And there's an axial load that's going to be applied down there. And what is this axial load? Okay, and this axial load will be action is equal to reaction. So it will be going this way, and it will be our PX direction. Okay, so it will be in the opposite direction. Okay, in the x-axis, on the x direction. So I'll draw my transformation again. This is x, y, and this is rotation about z. Okay, a lot of times, even seasoned engineer, they forget about px a lot of times. Okay, it's a common mistake that to be made. Okay, right. So some of you would tell me, Eugene, does px has to be acting on the centroid or of the centroid? Let's say this is our centroid. Okay, let's say this is our centroid. So let's say this is our centroid position, right? Or I make it that px is acting off the centroid. Okay. So this is our centroid. Okay. Now, does it matter? Question for you. Does it matter if it has to be aligned to the centroid for axial load? Can anyone answer that, please? Does it matter? Anyone? And if it does not, why? Okay, I'll answer for you. Okay, whether it's aligned to the centroid or not in px, it does not matter in terms of axial load. Now the next thing is why. Can anyone tell me why, please?
Can't you just account for it with like a moment?
For axial load, it's not necessary. Okay, any idea why, Marco?
No, I'm not sure.
It's okay. It's okay. Okay. Why is, if we go to the notes last week, okay, on Friday, how the axial load is distributed, right? It's constant. Yes or no? Right? So it's not a distribution, it's a vertical line. So it does not matter whether you have you have a, whether is it applied exactly on the axis or not. Okay, or at the center or not. For this case, okay, for the case that we're together. Later on, when we do another unsymmetrical, it does matter. For this case, it does not matter at all. Okay. Right. So from here, okay, I'm not going to find centroid for you. You guys know to find centroid. But one thing I want to highlight is this. Okay. For this problem, when you find your centroid, okay, I'll write down what is the centroid. But as I said, we will not determine. Okay, so our centroid y bar is equal to 8.15 millimeter from the top. Or if we were to determine from the bottom Okay, is equal to 11.846 millimeter from the bottom. Okay, so from the top, what do I mean? So this surface is over here. Is the top, and from the bottom, this is the bottom part. Okay. Now, why do I emphasize the preferred way? Okay, for this case is I will prefer to take it from the top. Okay, the preferred technique is yours. Okay, should take it from the top. The top is the preferred technique. Okay. Now the question is, why is that? Okay, why take from the top? Okay, because when we will calculate the moment is equal to P